Okay, I had a question about homework 10.2 here. So let's take a look at this. We've got a compressor, an evaporator, expansion valve, condenser, compressor, expansion valve, and evaporator. Now let's call the state 1, 2, 3, and 4, and the refrigerant's going this way on a TS diagram. It's going to compress from saturated vapor to state 2. It's going to follow a constant pressure line to saturated liquid, state 3 in the condenser. And then it's going to follow a constant enthalpy line back to this condenser or evaporator pressure. So this is a TS diagram. So this is a constant pressure line, this is a constant pressure line that would continue on like that. So what is given in this problem is T1, which also happens to be T4, and T3. So if we knew T3, we would also know P3 because that's saturated condition. So we can go to tables and this is R134A. Take me a minute to get there, and we're going to look for our temperature, which is 57 degrees. So right here, 57 degrees is, we're going to have to interpolate here, but it's going to be about maybe 15.4. If we were lucky, we'd say that it was 16. But of course, we're going to have to interpolate. Then that means that P2 is also 15.4. So we know this pressure now. Then we look up the temperature T1 is 12 degrees. And so for saturated vapor at 12 degrees, that one is in the tables directly. So we have saturated vapor, Hg rather, is 254.03, and Sg is 0.9132. So from that I get that S1 equals point, that again, 0.9132, and H1, which is Hg at 12 degrees, is 254.03. Right, so now I know that state 2, trying to find H2S, it's a function of S2 and P2, which it's really the same as being a function of P3, which is equal to Psat for T3. And S2 is equal to S1. So now we have values for this, and we can go to the superheat tables and find that enthalpy at approximately 15 bar. It's going to be between 14 and 16 bar. So as I was saying, if we were fortunate, it was 16 bar. Let's pretend that. And I'm looking for whatever it was, 0.9132. So 0.9132 would be somewhere here. Now, of course, it wasn't exactly 16, so it was between 14 and 16, like 15.4 or something like that. So I find 0.9132 here. I find 0.9132 here. I find the corresponding enthalpy here and here for those two pressures, and then I interpolate. Once I get those two enthalpies, I have one now at 14 bar, one at 16 bar, and I interpolate to 15.4 between those two values. So it's called double interpolation, but you do 3 interpolations to find it. I don't have the value for that. I think this is the example, so if I just put something in, I think it will tell me I'm wrong and give me the exact answer. So it's going to be 254.03, and that's the compressor inlet. Actually, that one I did find. The entropy 0.9132. That one should be correct. And then this one, I'm not sure what it's going to be, but I can make a guess. It's somewhere between these 4 values. So around, that would be about 280, and I'm going to say 280. It'll be somewhere around there. And of course, I'd have to do the interpolation to find out, and we get that it's 285.55. Now that's not the one that I interpolated for. This is H2S, and then I have that the compressor efficiency equals H1 minus, sorry, H2 S minus H1 over H2 minus H1. So the this is ideal work for the compressor over actual is the definition of the compressor efficiency. So the ideal is always less than the actual. So this efficiency was 82%. Then I solve for H2. So that's the one that's part C. So H2 equals H1 plus H2S minus H1 over the compressor efficiency. And that is what equals 285.55. The rest is pretty easy, so that was the hard one, finding H2. Then H3 is the saturated liquid value at T3. So I'll go back to the saturation tables. And T3 was 57, unfortunately. We have to interpolate a little bit. So that's at 56, that's at 60, so it's going to be about maybe 132. Let's try that. Should be close. 132.55. The evaporator inlet, well, H4 is the same as H3, so H3 is equal to HF at T3, since it's saturated liquid value, and H4 simply equals H3 because it's an expansion valve. So by definition, there's no work, no heat transfer. We're going to assume no change in kinetic or potential, and it's steady state. So same value, 132.55. Then finally, our coefficient of performance is let's use so the only work term is actually this is an air conditioner, so that's not an engine. Q in over work in. So our Q in is in the evaporator, and our work in is in our compressor. So we have H1 minus H4, of course, times m dot, divided by H2 minus H1, again times m dot, but that won't affect the efficiency. And I will have, so my H1 is 254.03 minus H3, 132.55. And then H2 is 285.55 minus 254.03. And this is about 122 over 30. So give or take about equal to 4. So let's try 4. And it's 3.854 exactly. So the cooling capacity is Q dot so just the numerator here with the m dot still in it, and the power for the compressor is just the work in. Hope that helps. And let me just give you an elevated view of that so you can see it all at once. And let's change the focus. And let's give you a full screen here. Alright, so it kind of maps out the problem for you. Hope that helps.